Welcome back, everyone. Let's get an overview of where we've been and where we're going. So today is the 29th. Is that right? Oh, it's the 28th. We're getting 29th would be Friday. So we're going to take a look at exponential and logarithmic equations. We're going to tie in the last three sections we've been talking about, which are exponential functions, logarithmic functions, properties of logarithmic functions, and now we'll actually be able to solve some equations using those. Next week we will look specifically at exponential growth and decay, so these will be application type problems, and then we're done with algebra as we slide into the new topic of trigonometry. And again, that's going to be a transition point where some of you may do better at trig than you did at algebra. Some are going to like algebra more than you like trig. And some of you will be just fine in either one of them. But in your calculus class, you will need both of those concepts. Trig is specifically where you get things that are sort of circular in nature, forces, springs, and those kind of things that act in a circular way. So that'll help out with that. Okay, so we'll get into 3.4 exponential logarithmic equations. However, I have a public service announcement for you. You might notice I'm wearing an orange shirt today, and it's not just because I like orange, although I do. I'm from Oregon State. But today is Orange Shirt Day for Native Americans, and it's to bring back reminders of the abuses of Native American boarding schools. Both my grandparents went to Native American boarding schools. They were picked up at their reservation in cattle trucks as kids when they were 10 and 12, taken over state lines, sometimes 3 different state lines. They were from North Dakota. Their last high school was Haskell High School, which is now Haskell Indian Nations University in Kansas. So here are these kids at Kansas. And I've got stories from my grandparents about what they went through. They survived. My grandmother's still alive. She's 102 years old. My grandfather made it to 86. That's a long life for their generation. Many that went to boarding schools as kids never made it out. So anyway, we like to get you to think about it. What I do on my part, I just want to be sort of forward, is why I'm in education is because of my grandparents, because of what my mom went through on the reservation school she went to, is to the basis for most of our education. Indian boarding schools were set up by the military. A lot of what we do in schools has dictated by what the military did for their training, discipline, and do this. Things like attendance policies. It's because they don't want you out there causing trouble, so that they force you to go to school, and if you're not in school, you lose points and those kind of things. School should be about the focus on learning. And if you're learning, does it matter whether you did it here or someplace else? As long as you're learning, you're there. So that's why I don't have a point system for whether you're here or not. I record, so if you're not here, you at least can see what went on in class and still learn, because that's what it needs to be about. So I'm always trying to revise my teaching to make it more humanistic, to give students more choice, because my grandparents, they didn't have that choice. In fact, they were even punished for using their own language. Neither one of them spoke English when they went to school. They spoke French. They spoke 3 different languages. My grandfather's French, Chippewa, and Cree, but not English. He learned it at school. So anyway, if you see a Native American person wearing an orange shirt, that's probably because they have a connection to that boarding school experience. Okay. And the goal is to make things better, not to dwell so much on the past, because it's painful to think about. We can't change the past, can we? But we can learn from it and make a better future for all. And apologize on, I did get one request. I know some of you do use the PowerPoints for your sort of notes, which is great. There are also the course notes here, but I'm always a little bit behind because the courses I teach. So a lot of times I'm just putting the slide decks together, or at least looking at them and beefing them up a little bit from my other course early morning before I come to class. And this one was in pretty good shape overall, but because in this class it's a STEM focus, we do a few more things. I added a few more examples that we can work through together. But you'll see it says Module 13. That's from my online course. This is actually, we're doing the section. But both courses were built off of the same sort of starting place. So they're very similar. But again, the STEM course is going to have more in the way of manipulations, algebraic manipulations and such. So we'll go there. Any questions or concerns or comments? Yes. Yeah. Yeah. So yeah, just keep working on the homework. I think what I've done, again, I forget which class, but this one allows me to put a setting that you can turn in the homework after the due date. So those due dates are there to try to help you stay on track. But if you get past it, you can still work on it. There's no penalty. The penalty is if you let too much pile up, then you have a lot, you'll lose a whole weekend because you got to catch up on a couple weeks worth of work, right? But sometimes we have to do that. I have to go do this weekend, so next weekend's going to be a big one. So I try to make it so that you can do that. So today we're going to focus on solving equations. So we've got this equal sign, and we've got statements on either side. We're solving for the variable. So we'll pick up a few different techniques. One technique is with exponential functions. Since exponentials are a one-to-one function, right? Each x has only one y, and each y maps back to only one x, right? So they are, again, exponentials would, be something like this. Since they're one-to-one, what that means is if we have the same base, say 4 squared equals 4x, that the only way these two things could be equal, again, these are two outputs, is if their inputs are equal. So what that allows us to do is say, well, if 4 squared equals 4 to the x, then 2 must be equal to x. The inputs are equal. Okay, so that's what we're going to do with this one. But we don't have 4 to the x equals 4 to something, but how could we rewrite 64 as 4 to some power? Can it be written as 4 to some power? Yes, sir. 4 to the third. You might need to use your calculator. I probably would. 4 times 4 is 16, times 4 more is... That's the only way we're going to be able to do these particular ones. So if we had 65, we'd have to use one of the other techniques. But with 64, that's 4 to the third. So what is x equal to? X has to be equal to 3. Because it's saying that the outputs are equal. It means that the inputs have to be equal. So far, so good? Okay, the hardest part was recognizing that 64 is 4 to the third power. You may not recognize some of these numbers right off because we didn't memorize an exponential chart. We memorized maybe multiplication tables up to 10 or 12 or something, but we didn't memorize exponential charts. No, okay. So, like this one, I have no clue, but if it's going to work, it's got 2,401 has to be 7 to some power, right? So I would just start 7 times 7 times 7 and see how many times I have to multiply by 7 so that I can rewrite this as 7 to the x equals 7 to the what? I need some help here. I didn't memorize my exponential tables. Of course, you keep 7 times 7. 4 or is it 5?
I think it's 1, 2. Okay, now I just messed up.
4? Yeah, I figure it'd be either 4 or 3. I think 3 is 343, so maybe, yeah. Um, and again, sometimes with the calculators, you'll, show those who's watching this on the video. All we're doing is 7 times 7, so that was 2 times, nope, that's not it, times 7 more. That's not it, but you sort of start to see this, and then if we do it one more time, 2,401. Okay, have to keep track of it. There we go. And so our answer, x equals 4. Exponents are equal. So that's all we got to do. So that's one method. You'll see some. Again, if they aren't the same base, then we're going to need some other tool to do it. But if they are the same base, we could do this. We could also graph these two things, right? I'm again just showing you all the methods. So 7x to the 2,401, what would that look like? We would go to Desmos. So again, we could graph one as y equals 7 to the x. That's that exponential function. The other one, y equals 2,401. And again, what I want to do is, so if y is 2,401, I'm going to need to see that high, so the y-axis has to go up at least that high. Let's go to 3,000. Then you see the point of intersection, and you see when x is 4, y is 2,000. That's the intersection point, so x equals 4. Okay, that point of intersection. So we can solve these. All these ones we're doing today can also be solved graphically. You graph the left side, you graph the right side. Where they intersect will be your answer as well. So again, another way to, but then this way you could also visualize it, right? You could also see when x is going to be 5, that's going to be way up there. So you kind of see what's happening with the exponential. So far, so good? All right. Let's get to another technique using what I call the log dance. And what is the log dance? We're going to convert the exponential to a logarithm function. Again, it's not really a calculation, it's a dance. So if we have some base, say to some exponent equals some output, the log dance takes that. Remember, the base stays the base, so we'll get the log base b. And what goes inside the logarithm? The y. So we know it's either x or y, but the x and y, or the b and the x are together, and that's going to be equal to x. Okay, so that's the log dance, is just kind of this inverse. There's 3 things in a mathematical fact. 2 numbers that are either multiplied, added, whatever, or in this case exponentials. We got an answer. When you do the inverse, they switch over. So let's see how that's going to help us. Again, if this was 5x equals 25, we would just take 25 as 5 squared and x equals 2. We see this is a little bit less, so we can at least get an estimate, right, that x is going to be close to 2, but it's going to be a little bit less than 2. And we can get this through, again, what we call the log dance. We can rewrite this as log base 5, right? The base stays the base, so that's, and then now these guys got to switch places. The 5 was with the x, so it's now got to be with the 21. It almost looks like 5 to the 21 power, so that's, I think, maybe why they did logarithms with a base on it. is now going to be equal to x. Notice we have solved for x, but we didn't do any sort of algebraic other than doing what to me it seems more like a dance. You're moving things around. Well, what's log base 5 of 21? Again, we could use a calculator to get a numerical value, but remember it's going to have a lot of decimals. Sometimes if they want an exact answer, this is it. This is an exact answer. If they want an approximation, that's when we put all the decimals in. But yet it feels when we put the decimals that's more accurate, right? Because it's got a lot of decimals. But with logarithms, you don't get repeating decimals. You get them going on for a long, long time. You can't stop it. So it's only exact here. But let me also go here. Just as a reminder, we can use our other calculator. Remember, you could use the change of base if you don't have a TI-84 or one that allows you to do the change of base. Let's see this one. Turn my plot off. What did we have? Oh, we want to go just to the screen here. We go to math and we arrow down till we get log base. And then we can enter log base 5 of 21, and you'll see it's going to be probably 1.9 something, maybe 1.8 something. It's going to be close to 2, 1.89, pretty close. But you see it's not exact. We have to round it at some place. But if they ask you to round it to 2 decimal places or 3 decimal places, you can use the calculator to do that. Remember, you could also, if your calculator doesn't have that feature, you could use the natural log of 21. This is the change of base formula divided by the natural log of 5, and we'll get the same answer. So depending upon which system you have. I like it just using log base because it looks like what you see. And again, we could also do this graphically, just showing you 5 raised to the x power. And the second y we're going to say is 21. So we're graphing both sides of the equation. Where's the answer going to be? Wherever they cross. So I'm going to go zoom. Standard. Actually, let's try this. Sometimes it works well if you do a zoom fit. Sometimes it's not. It's zoomed out too much. So I'll go back to my window. We know the answer is supposed to be like 2, so change my window a bit. And Y max, let's go up to 25. This should do it. So sometimes we got to find it, but we find our point of intersection. And again, you can do that with your TI calculator by going second calc. Number 5 is intersect. And the way that works is it will go to the first curve, and it's actually right now it's on the blue curve. You don't see it, but I'm just going to hit enter. It jumped to the second curve. You now see the little cursor. I hit enter. It asks for a guess. I hit enter again, and it gives us that answer, the intersection 1.89166, which was sort of the same thing we got. Okay, but I just multiple ways to get to the answer, and it's helpful if you actually look at all of them, because again, the graph gives you more information. It gives you how the function's changing and everything. You doing okay? Go ask that guy they can clean after class, can't they? Hopefully it'll just be another short period of time. Okay. So that was a simpler one. Let's go through a few of these. It's kind of going to be the same process. We won't necessarily go look at every way of solving it, but we'll do the same thing. So we've got this function. It looks like it's going to be a little bit of, can we do the log dance at this place? No, we've got to isolate. Before we can, we have to isolate the exponential. So what could we do to isolate the exponential? Okay, so the two steps, we're going to subtract 5 and then divide by 4. Good. That's 28. And then we'll divide by 4 on both sides. So we get 3x. 28 divided by 4 is 7. And now we can do the log dance, right? 3 is the base, so this is going to be log base 3 of 7 equals x. Notice we have it solved for x. Again, if they want the exact answer, that is it. If they want an approximate answer rounded to 3 or 4 decimal places, we plug it in our calculator and we get that. But I want to focus just on the technique. Is we okay with that so far? Okay, good. And we got one last one, e to the 7x plus 9. Can we do the log dance on this thing? Not sure. Why not? Let's try. And actually we can, because the exponential is isolated. Now you may be looking at that 7 times x. You're going to see we're going to have actually an extra step here. But and e is kind of a weird one, right? But it's log base e. I'm going to do that as log base e. You could write it as ln, because that's what it is. But I'll start with this, just saying that that's its base. 9 is the input. 7x is the answer. Have we solved for x? Not yet. Almost. Because we got 7x, but we need just x, so what do we need to do now? Divide by x? No. We want to solve for x, so we divide by 7. So that's now it. And we get x equals, I'm going to write the log base e in its regular form, natural log of 9 over 7. And again, if they want an exact answer, this is the exact answer. If we take the natural log of 9, we will get some sort of decimal that goes on, and we're going to have to round it at some place, so that's an approximation. But sometimes they want that, especially in engineering. Go find that on your ruler to measure something, right? Oh no, you got to get the decimal. Yes. Good so far? Okay, so we've got exponentials. We could get them to be the same base, and then the exponents are equal. We can use the log dance if we can isolate the exponential and then do the log dance and use logarithms to solve. And then we can also get it to work the other way. So if you can do the log dance, you can do the reverse log dance, right? So if we've got logarithms, we can turn them into an exponential, and a lot of times that will solve for x. Okay, so we've got something like this. Can we do a log? If we did the log dance, what would we get going backwards? So this is the base of an exponential, right? Which one of these is the exponent? Good. The other two. This is our exponent. And it's equal to the input of the logarithm. We're not done yet, but now we've got it. Notice there's no logarithm. We can get it. We know what 2 squared is, right? It's 4, 2 times 2. So we could write that. And now we just have a linear equation which we can solve and subtract 9 from both sides. And 4 minus 9 is -5 equals -5x. We could then divide both sides by -5. And we get x equals 1. Really? All we have to do is put in 1 for x, and that's what our solution is. Wouldn't have seen it coming at the beginning, but plug in 1, that's 5. -5, that's 4. So log base 2 of 4 is 2, because 2 squared is 4. Okay. Not so bad. So the log, we can take a log and turn it into exponential to log, and again, a lot of times that's just sort of the easiest way to solve it. This one, can we do the log dance at this point? 5 to the -14. Something's in the way, right? There's this thing in front of the logarithm that we want to isolate the logarithm first. So we will go ahead, actually divide by -7 first. -7 divided by -7 is 1. So then we have log base 5 of 4x. 14 divided by 7 is 2, positive 2. So now we've got the logarithm isolated, and we can do our log dance, right? We can change it to an exponential. Base 5, so that's 5 to what is going to be our exponent? The 2, the thing on the other side, and that's going to be equal to 4x. We know what 5 squared is, or we could figure it out with our calculator. 5 squared is 25 equals 4x. Divide both sides by 4. So x is equal to 25/4, which doesn't reduce down. We could just leave it at that. If you want, you could take 25 divided by 4. It's not too bad of a decimal. What is it? 6.25? Because 24 divided by 4 is 6. So it makes for a nice decimal. That's fine. And that's still an exact answer, right? Because it's not we didn't round. So that's still an exact answer. How we doing so far? Making sense? And notice we haven't had to apply our logarithm properties yet. But that's probably next, isn't it? I think it is, if I remember right. Oh, no. We'll do specifically the natural logarithm, which remember is log base e. Same thing going on. Can we do the log dance at this point? No, because the 3's in front. So we're going to divide by 3 first. And we end up with the natural log of 6x equals -2. Then we can do the log dance. Now, because it's ln, natural log, logarithm naturel, right? Actually from the French, we just have to remember that there's really a base e here. So when we do the log dance, we get e to the -2 equals 6x. Okay, so that's just, we're able to do that. And again, you're thinking, what's the mathematics we did? Where did everything go? It's the property of inverses between exponentials and logarithms. And again, I call it that log dance because we move things around, but that's how things are defined. Now, e to a power, remember e is this number like pi. It's non-repeating, so it's got decimals going on. Again, a lot of times, especially in engineering, you want to have an exact answer. And the reason we want that exact answer is when we send it over to the guys, the factory who's going to make it, it allows them to get their level of precision that they need. Because with this exact answer, if we round it to 3 decimal places, they could do that. Maybe they want more precision. They want to go to 5 decimal places. They can then figure out what they need to do. Okay, we haven't quite solved yet. We divide by 6. So this one we get x equals, and again, this e to the minus 2, since it's negative, you could put it down. So you could rewrite this as 1 over 6e squared, which is the same thing as e to the negative 2 over 6, whichever way you want to write it. But a lot of times they will ask for your answers to be with positive exponents. So just recognize that those are the two ways you could write it. Is that good so far? Okay, awesome. Now, what if we got logs on both sides? So notice this is just a bunch of techniques to solve. And then again, we'll get to the applications next week. Oh, that gave me a headache. Too many logs on there, right? How can we solve this thing? Well, if that 1 wasn't there, they're both log 5, and just like the exponential, I could say, well, they're 1-to-1 functions, so if the outputs are equal, the inputs have to be equal, but I can't quite do that because of this 1 is there. So, any suggestions? Get the logs on the same side, right? That's, if we get those logs together, remember we can then do log properties, because they'd either be added or subtracted. We can make them into one logarithm, and then we could do the log dance. So that's the process with these. Get the logs together, use logarithm properties. So since there's a 1 over here, I'm going to add log base 5 x minus 6 to both sides. So over here it cancels, and what we're left with, I'm going to write this as log base 5 x minus 6. So that's the 1 because it's positive, and then I'm going to subtract log base 5 of x plus 2. It's all equal to 1. Now I can use my log property. So when I've got 2 logarithms that are being subtracted, what does that become as a single logarithm? Do we multiply them or do we divide them? Subtraction is division. Okay, so there's that connection. If it was addition, we would multiply them together. Subtraction, we're going to divide them. The positive one's on top, the negative one's on the bottom. Oops. There. And that's equal to 1. And we're not done yet. We haven't solved for x. So, but we can do the log dance now. 5 to the first power, right? Change it to an exponential. 5 to the first power is just 5. It's equal to x minus 6 over x plus 2. Now when we get done with this, we're going to need to talk about domain. What can we not put in a logarithm? What gives us an error in a logarithm? Negative numbers or even 0. So sometimes we'll get an answer, but it won't work because if we plug it in, we get a negative answer or we get 0. So you've got to be careful with these ones, kind of just like I think on one of our tests we did. It was asking for vertical asymptotes, and one actually canceled out, and one was actually a hole instead of a vertical asymptote. But same thing with this one. we might get an answer, but it might not work. So we got to test them. So we'll see. Um, so okay, yeah, we got this part. So we've got 5 equals this. We want to solve for x. Maybe multiply both sides by x plus 2. And this cancels with that. We could distribute the 5. 5 to the first is just 5. So this side we get 5x plus 10 equals x minus 6. And again, just algebra from this part. We could subtract x from both sides. So whenever we have x's on either sides, we get them together. At the same time, just to save us a little space, I will subtract 10 from both sides, simply because I know the x is going to get over here. 5 minus 1 is 4x. This becomes 0. Negative 6 minus 10 is negative 16. This is 0. Divide both sides by 4. X equals negative 4. Did I do that right? Does anyone see anything, any glaring mistakes? Usually you let me know as I go, because you know I get too far. Now let's check, does this work? So we have to come up here. Can I plug it into this one? I get negative log base 5. Negative 4 plus 2. Uh-oh. That looks like a problem, right? Because I'm going to get negative 2. I can't get an answer. That's undefined. Boom, we're done. We don't even have to check. I could check it over here, but if I put negative 4, I'm going to get negative 10. Dang. Means this can't be solved, can it? That's why I'm thinking I did something wrong. But this is negative. That's negative. I added this over here. It's equal to positive 1. See, if we put it up here even, it's not going to work. We're going to get negatives. Oh wait, we get a negative over a negative. It would work here. But the fact is, it wouldn't solve this equation because it's not in the domain, right? Anything less than negative 2 is not in the domain. Actually, anything less than 6 is not in the domain because of this side. So I guess we're stuck. Answer is, does not exist. Again, unless I made a mistake somewhere in there, and it should be positive, but it's even positive 4 wouldn't be big enough, right? Because 4 minus 6 is negative 2. That's not a valid input. Anywhere in a math statement, if you get an undefined, the whole thing's undefined. Because what's 2 plus undefined? Well, it's undefined. So, does not exist. This always frustrated me. I go, why do they make me do all this work for something that doesn't exist? But what we could do is also we could graph these. And what we would see is that these don't intersect. There is no way, there is no number to get an intersection between these two sides. Actually, I don't think we have too much to go. Let me verify that, because sometimes when I do that, I'll say, wait, there is an intersection, so I must have made a mistake. Or if it's not, then I feel better that I did all the right work. So let's go ahead and put this into Desmos and see if we get an intersection. And if we don't get an intersection, let's see, what was it? It was negative. Desmos has these functions that you just have to scroll down, and they've got log base right here. So log base 5 of, what was it, x plus 2. So that's one graph. Let me we're zoomed way out, so let's yeah, I think that works. So that's what that graph looks like. Get rid of that one. And then on the other side, we had y equals 1 minus log base 5, and that was x minus 6, right? And what we see is, you know, they're not going to intersect each other. If they would, it'd be down here, but they're kind of going to run parallel for infinite, you know, there's no intersection. This is sort of makes me feel better. There's no answer. There is no intersection. So maybe you want to graph them first to see if there's even going to be an intersection. If it's not, you can say, okay, that does not exist. Work it through, however you want to do it. But notice that if we do these two things, I now feel much better about my answer. Otherwise, I'd go away still have a little bit of stress. Did I just miss a negative somewhere? But this helps me. I'm going to go, yeah, we come out here, they're parallel for a long, they get closer, but they're never going to intersect. I feel pretty confident now. Which is good because you guys got a grade on the line, but I got a job on the line. If I make too many mistakes, I lose my job. So we want to be, and that, you know, when you're an engineer, you want to be able to check these things before you tell the boss, because you don't want the boss finding errors in your work. You want to find them before get them fixed. Okay, we don't got too much more. Oh, we do have this one. Oh, this one is, let me give myself some space here. If I can move this elsewhere. This one we won't need as much space. Okay, so these are natural logs. What we can do is we can use the property of logarithms. So when we're subtracting, when we combine this side into one logarithm, what do we get? X minus 6. Do I multiply or do I divide? Divide. Good. And this one, notice I didn't worry about bringing the other logarithm over. We could have, but now that I've got natural log equals natural log of something else, right? Natural logs are one-to-one functions. So this is saying the outputs of these two are equal, the same function. So what that tells me is that the inputs have to be equal. Notice how I can just sort of do that, and it seems like, what did he do? I dropped the logarithms because it's just the insides have to be the same number if the outputs are going to be the same number. Does that make sense? Kinda. Still feels like Little Crow's making up his own rules as he goes. Bless you. But it is. It's the property of one-to-one functions. Okay. So now we need to solve this. Multiply both sides by 2. We get x minus 6 equals 40. So add 6 to both sides, you'll get x equals 46. We do a quick check back here. If I put 46, that's going to be 40. We're all good. These are all numbers. Natural log of 2, natural log of 20. So it's within the domain. So that's a valid answer. And again, you could do it by graphing both sides, and you would see that these two functions, the two left side and the right side, would intersect at x equals negative, at x equals 46. But again, you got to be careful of these. This is something I would forget to do, is when you get your answer, check it, because it might not work with these processes that we're doing, because we're, you know. And again, if we graph it, we see, oh, these are ones that are running parallel. There is not going to be a solution, or something else is going on. So a lot of times the graph is very helpful. We see we've got and also see x equals 46. That in my standard window, I usually only see to 10. I wouldn't know to go look when x is 46, except I solved it first, and now I could go to the graph and say, okay, I got to maybe make x equals 50, and then I'll be able to see this intersection. Okay, so that's the thing that the algebra helps with. I'm trying to slow down because we're going to get done way too early. I still got a little bit of it. Okay, so now we're going to start putting it together with another exponential equation. How would we go about solving this one? Move the 2 over. Good. So let's isolate the exponential. Nine minus 2 is 7. I can't get 7 to be 4 to some power. If I did, I could say the exponents are equal, so I can't use that one. Did I?
Wouldn't it be 4 to the 3x plus 1?
Thank you. See, those are the types of errors I said, that looks fine. Oh, it's 3x plus 1. You'll even see on some of my videos, and sometimes I don't get a chance to go back and change them, but I make copy errors. Because see, I saw this 2 instead of that 1. So thanks. Don't let me get too far. And that's what you'll find, and those are the frustrating ones, because you know you did everything else right, but you're not getting the right answer, and then you think, I must be really blowing it. No, I just copied down something wrong. What do I do next? You could take the ln of both sides. You could do the log dance, since we've been doing the log dance. So one way is to say that this is log base 4 of 7 equals 3x plus 1. We can also, let me change colors. Do something which is called, taking the logarithm of both sides. And if we have a logarithm of something to an exponent, what do we get to do with that exponent? So this is a property of logarithms. We're actually able to bring this down here. Okay. Again, we sort of addressed it here, but either way, the log dance is kind of what I like. But other people, they like to take the natural log of both sides. So I'll show you both, and you pick which one you like best. So we get 3x plus 1. Now be careful, that exponent is all one thing. It's all times the natural log. If you don't put those parentheses, weird things may happen because you just apply it there or something. So just it's one whole group. Natural log of 4 equals natural log of 7. Again, what is our goal? Our goal is to solve for x. This. Okay, so what should I do? Well, let's get the logarithms onto the other side. And one of the things my teachers always told me is, when you get natural log of 7, those are numbers. Those are no longer functions. They're no longer variables. They're a number. But we leave them that way because they're not a very pretty number. Okay?
Why would you take the natural log of both sides?
So that because when I do that, first of all, it's 1-to-1 and it's legal, so just like I would add a number to both sides. But when I take the natural log, it allows me to bring that exponent down. You could use any log you want. You could use log base 10. Okay. It would still work. We use the natural log because ln is a shorter thing to write. You can script it, but it's usually one of the keys. Some calculators like the TI-8092, they don't make it anymore. It only had the natural log button. So if it was that, so usually most calculators will have it. But it's, again, yeah, we could have used any log. And so we end up with this. We get 3x plus 1. I can now take the parentheses off, but on this side, it's the natural log of 7 divided by the natural log of 4. Okay. Solving for x, again, sometimes I get going, I said, what am I doing? Solving for x. So that's why I come back, I highlight what I'm trying to do because I forget, right? Now what do? Subtract 1 from both sides, subtract 1 from that side, and then we're going to divide by 3. But let's do that in 2 steps. Natural log of 7, natural log of 4, minus 1, and then divide by 3. Again, we've got to divide the whole thing by 3. So sometimes when you do this, you get these sort of funky answers. Oops. And see, I did it. I was going to reverse them. It's natural log of 7 over the natural log of 4 minus 1, all divided by 3. It's not a very pretty answer. Again, you could plug it into the calculator, figure out the numbers. You won't get an exact answer, but if you have to round it to 2 decimal places, 3 decimal places, you could do that, right? But that's one way to go. You could have done it this way up here. Again, if we want an exact answer, you subtract the 1 and divide by 3. So 2 techniques. Either the log dance. I typically will, personally, I like the log dance. It gets me that. And in my calculator, I have the log base, so I can take that just as easily. I have access to it just as easily as taking the natural log. Okay, but any questions on that part, that technique? Okay, so one thing is when we've got the exponent up there, if we take either the natural log or any log, you'll just find we'll use natural log because it's just typically what they will show. That will be okay. Here we have 2 exponentials. Let me kind of get rid of this. Just that nobody will make it smaller. Okay. So what could we do with this one? We could do the same thing, take the natural log of both sides. And the reason we did that is what property do we have when we have a logarithm? We can use the power principle that the exponents can become multiplication in front. So this becomes x plus 5. Remember, the exponent is all one thing. Natural log of 3 equals 2x minus 9, natural log of 7, not a lot of fun to solve. It's going to get a little messy, right? We could distribute, because we got to get to the x's, right? And I think that might be the best. It's a route. There might be a shorter route. Sometimes with algebra, there's more than one way to approach something. So sometimes we just got to try something. And yeah, so let's distribute. So we get x natural log of 3 plus 5 natural log of 3. And notice 5 natural log of 3 is really just a number. It's no longer a variable. We distribute the 7, our natural log of 7. So that's going to be 2x. I'm going to put parentheses around the things that are in the natural log. Just makes it. I might have to erase some of this other stuff so we have room. Again, what is our goal? is to get x by itself. So there's an x, and there's an x. Nothing else has an x, so get everything with an x to one side, everything without an x to the other side. Again, just kind of, so I'll move this one over, because that doesn't have an x, and I'll move the one with the x to the other side. Could have gone the other way, but it might have been smoother. So that'll cancel here. Minus 5 natural log of 3. This is minus 2x natural log of 7. This is all up recorded, so this stuff has been done. Let me just get myself, I need some more space, so we're going to steal all this room. Okay, that becomes 0, that becomes 0. So we have x natural log of 3 minus 2x natural log of 7 equals negative 9 natural log of 7 minus 5 natural log of 3. Oh boy, what do we do next? We want x by itself. If I had xy plus xz, what could I do with those two x's? Couldn't I factor them and end up with y plus z? So this is I call it undistributing because it's a little less natural than distributing. But so the step is we distributed. Now we need to undistribute that x. So what we're going to do is we're going to move the x to the front in both cases. So we get x, what's left behind, natural log of 3, that's from this term, minus 2 natural log of 7 equals what was already over here, minus 9 natural log of 7 minus 5 natural log of 3. I'm going to give myself a little bit more room over there. And then what do? We just need to divide by all this stuff being multiplied by the x, right? Divide by this. So we're going to get x natural log of 3 minus 2 natural log of 7. That's going to cancel. Our final answer is going to be what was on the other side. 9 natural log of 7 minus 5 natural log of 3 divided by the stuff over here, natural log of 3 minus 2 natural log of 7. And again, this is just a number. We could enter it all in. It's all numerical values, and we could get a approximate answer. This is a version of the exact answer, assuming I didn't make some error somewhere, which is always possible, right? But I got you guys watching my back, right? You got me. Yes, sir.
Is that the farthest we're going to need to go, or is it going to look us to get one step further?
It depends. If the homework answer says give me the exact answer, that's it. If it asks you to give the answer rounded to so many decimal places, then you're going to want to plug that in a calculator and get actually that approximate answer. I hope that's the last one for today, because I think I used up all my brain energy on that. How's that? Okay, we'll see. I think there might be one. There's this. Forgot about these guys. But this is a little bit lighter fare. There will be some questions. Where do we see exponential functions? finance type problems. So I think in 3.1 you might have had some, at least in the textbook they did. I don't know if we did them or not, but I did see the need for, we might need these. So this is the what they call the periodic compounding. So n is how many times a year they compound. So if it's monthly, n is equal to 12. If it's quarterly, it's equal to 4. So that's one. And then this is over here is the formula if we have what's called continuously compounding interest. And that's basically, it's always compounding continuously. And we have those two types of growth. Some growth is so fast that they use the continuous formula for it. Others sort of have cycles. And so that's when we would use a periodic. The A is the future amount of the investment. P is the principal or the amount of the deposit. In the first formula, N is the number of compounding periods, and R is the rate, the interest rate as a decimal. T is the time. Okay, and we'll do. Yeah, we got enough time. We'll do one example. Okay, and again, you'll be asked to do one or the other. This one they're asking. A lot of times what I'll do is I'll sort of look back, read sort of backwards. So I look at the back. Oh, they're compounding quarterly because that helps me know what's going on. I got an interest rate. How many years will it take for an investment of 2,000 to grow to 2,400? So I know the amount of the S. So this 2,000, what letter is it? A, P, N, R, T. It's the P. So that's the principal. That's the amount of the deposit. 2,400, that's the future value. They use A for that, the accumulated value. This number here is the rate. And it doesn't tell us directly, but since it's compounding quarterly, what that tells us is that N equals 4. And we're doing it periodically. If it was continuously compounding, then we'd use this formula. We might do both. So anyway, we plug in all our values. A is 2,400. The principal is 2,000. 1 is a number plus the interest rate, 2.41. So that's going to be 0.0241 divided by the number of compounding periods, which is 4 quarterly. And the exponent is going to be 4t. Because it's quarterly. So I'm just following this formula to get through. Now, so that was the first part, is getting it set up. Now I use any of the techniques that I want to use that we've talked about. It's always nice to isolate the exponential, right? So we could divide both sides by 2,000. And that's going to give us 1 plus 2,400 divided by 2,000 is 1 point something. 1.2? Okay, makes sense. Notice we're getting lower. For t, I don't like t's because I might write it as x, but we'll keep it as t's. But now what should we do?
Which is the natural log forms?
Yeah, natural log of both sides. That's a typical way to do this. We could use the log dance, but then the base is, yeah, I wouldn't do the log dance. So natural log of both sides is the typical way to do this, textbook way. And when we take the natural log, what happens to our variable up here that's in the exponent? We get to bring it down in front. So this becomes natural log of 1.2 equals 4t times the natural log of 1 plus 0.0241 divided by 4. And again, you could actually divide this and add 1. Might make it look a little prettier, right? Let's go ahead and do that. Let's see. So we can go, we'll take 1 plus 0.0241 divided by 4. That's 1.006025. Notice how we get a lot of decimals. Again, depending upon how much accuracy you need, you may want to have all those decimals there. So I could rewrite this now. It's the natural log of 1, what was it, 1.006 2. Say that again? 0.25. Okay. Again, just to, so I can be as accurate as I can be. 4t is out here, right? And what do we do to solve this? Well, again, we want the t by itself. So what we will do is we will divide by the 4, and we'll divide by natural log of 1.006025. That cancels with that. That cancels with that. And so our final answer is going to be natural log of 1.2 divided by 4 times the natural log of 1.006025. That's what t equals. And hopefully, and what is t? T is amount of time. It should be greater than 1 because we start with 2,000. We're going for 2,400. So how long does it take to get $400 in interest? Well, that's where we want to plug this in. And the reason we go with natural log is because, again, we usually have a button that will do that. 1.2. And I want to show you this one because you want to be careful how you enter this, because if you enter the 4 and then the natural log, you may get order of operations and it doesn't work right. Everything has to be in the denominator. So this was what, 4 natural log of, what was it, 1.006025, and then one more parentheses so that everything's in the denominator, and we'll hit enter. About 7.5 years, 7.6 years if we round it. Okay, so just be careful, and sometimes I get some really weird answers and they go, 200 years? No, it's, you got to get your parentheses in the right place. So look for order of operations. It's it happens. Sometimes to overcome it is if you go alpha F1, which is this y equals key, they give you the fraction, and so you could do it this way, and sometimes, and so then it's, you know, the numerator and denominators are all going to behave properly. Okay, but that's the last one we have for today. If they ask for continuous compounding, that formula is there. You would do the same thing and go from there. Okay, ready for a good weekend? Anything big happening this weekend? I hope not. It'd be nice to have a quiet weekend, right? All right. Take care.